So in addition to the geometries and bond angles that you need to know for groups with 2, 3, and 4 electron domains, in the HL class, since we've learned that things can expand beyond the octet, we also have to know about electron domain geometries, molecular geometries, and bond angles for groups that have both 5 and 6 electron domains. The concepts remain the same as before, but you just have more shapes to know about and more bond angles to be able to figure out. So there are 2 more electron domain geometries to know. When there are 5 electron domains, the way that they will repel each other, according to VSEPR theory, around the central atom is into what's called a trigonal bi-pyramidal shape, essentially 2 trigonal pyramids on top of each other. So if you look at this shape here, you end up essentially with what looks like a trigonal plane, so basically a triangle base in the center, where all the bond angles are 120 around each other, 120, 120, and 120 around for those 3 atoms across the middle plane. And then you have one atom that goes straight up, and you have another one that goes straight down. And so for these ones, they are 90 degrees off of that trigonal plane here, as well as this one. So there's a 90-degree bond angle as well, and then there's actually, if you consider the 2 that point up and down, there's a 180-degree bond angle between those 2. So the 5 one ends up being the most complicated of the shapes to try to remember in terms of the bond angles anyways. You've got a 120 bond angle, you've got a 90 bond angle, and you've got a 180 bond angle, actually all within the same structure. Okay, this is called trigonal bi-pyramidal for the electron domain geometry. For 6, it's a little bit simpler. For 6, they all spread out evenly, and it's octahedral is the name of the shape, because if you made a 3-dimensional shape around it, it would have 8 faces to it, 8 sides. That's why it's called octahedral, which is a little confusing because we're talking about 6 electron domains, but the shape it would form would have 8 faces. So octahedral is pretty straightforward. It's like an XYZ axes where they're all meeting. And so every single angle is 90 degrees. I suppose you could consider it 180 if you considered the angles across from each other. But generally speaking, all the angles are thought of as being 90 degrees from each other. So they spread out evenly, octahedral. So there are obviously going to be more molecular geometries than electron domain geometries. When you have 5 electron domains, depending on the number of lone pairs, if you have no lone pairs, your molecular geometry is also called trigonal bi-pyramidal. If you have 1 lone pair, then the shape that remains is this sort of, it's got 4 groups off of it, so it's a bit tetrahedral, but it's kind of a strange tetrahedral. It's not symmetric, and it's actually referred to as seesaw. If you were to draw 2 of the groups like this, and then the other 2 groups sticking out like that, it would sort of look like a seesaw that could teeter back and forth. And the 5th group is a lone pair there instead of a 5th bonded atom. So when you have 1 lone pair with a molecular with 5 electron domains, you end up with a seesaw shape. If you end up with 2 of the groups being lone pairs, then you end up with what's called a T-shape. You end up with one of the bonds remaining from that trigonal plane we talked about, and then you still have the one sticking straight up and down, and that forms essentially a T shape. You can actually have examples where there are 3 lone pairs, and so that only leaves 2 bonded atoms, and anytime, well, you can see that those 3 are going to kind of repel evenly around that trigonal plane, and you'll end up with this one going up and down, and that ends up linear. So we have another option for getting us a linear molecule, this time with 5 electron domains. So those are there are actually 4 different shapes possible from 5 electron domains. And for 6, there's going to be 3 different shapes possible. So octahedral being the first. If one of those things ends up being a non-bonding electron pair, that leaves behind what's called square pyramidal. It leaves that central sort of square plane between what we might call like the X and Y axis, and then still one of the atoms is pointing up. So this is like a traditional pyramid, like the Egyptian pyramids, a square pyramid, a square base, all pointing up to one top point. So that's how we name that shape. And here we have square planar. So if you have two lone pairs, the lone pairs are going to go as far away from each other as possible. Therefore, they're going to go on opposite sides, and that leaves behind this square plane here. And so that's why this shape is called square planar. In terms of what's going to happen to the bond angles, well, we do know that the non-bonding pairs repel more than the bonding pairs of electrons. So if the bond angle was here was 120, now when I have this lone pair, we would expect this bond angle to shrink down to about 117, something a little bit less than 120. In terms of this bond angle here, well, before this angle, if we go straight up and down, on this side, this whole thing was about 180. But now, since we have this lone pair pushing it, we would expect the angle on this side to be a little bit less than 180, probably 175, 177, and the angle on the other side to be a little bit more than 180, where it pushes those away. So remember that non-bonding electron pair is pushing more than the bonding pairs are pushing back. And so although I've drawn this as a perfectly flat line here, the shape would actually, those would be pushed a little bit off of that straight line. So the angle on the outside here would be more than 180, and the angle between them would be less than 180. So if you continue on, you just continue to apply that rule of that non-bonding pairs repel more than bonding pairs of electrons, and angles should therefore get sort of changed by approximately 3 degrees. So usually we think of it as getting squeezed closer together by 3 degrees, unless you consider what's happening on the outside of it, and then it's expanding it by about 3 to 5 degrees. For linear, down here we'd have 180. For T-shaped, it looks like it's all 90 and 180, but in fact, because of these lone pairs, we would expect that it's actually going to be a little bit off from perfectly 180. So you might be able to predict slightly smaller than 180, slightly smaller than 90 because of those non-bonding pairs. In octahedral, all the angles start off at 90. And in square planar, they're actually all 90 as well, because the influence of the two groups just cancels itself out. And so all of these have 90-degree bond angles. With the square planar, you would probably expect the angles to be slightly smaller than 90, at least within here, because this non-bonding pair is pushing up on the square plane, and it's going to push it a little bit closer to this top atom here. So in this one, we'd expect slightly smaller than 90-degree bond angles. So there's a lot to remember when it comes to VSEPR, but the underlying concepts really are the same. Draw the Lewis structure, count the number of electron domains here, and from the domains, you start off with there are 5 possible electron domain geometries: linear, trigonal planar, tetrahedral, trigonal bi-pyramidal, and octahedral. And then from there, you have to decide how many of those domains are lone pairs, and those lone pairs will change the name of the molecular geometry to something else. They will also influence the bond angle by causing additional repulsion, which usually we think of as squeezing bond angles closer together. So there's sort of a summary table here, and we'll print it out, and we'll spend lots of time trying to remember all of these names in class.